Hello, I'm François Schmidt, Research Director at CNRS, and this short presentation is about ocean turbulence and models. So first, I will give some numbers that I used as indicator of the state of turbulence. And for this, the first one is the Reynolds number. So this short video is useful to explain what it is. So it's put it here.
Which is attached to a container, is carrying water. At some point in the pipe, a colored pigment is introduced into the flow. A man called Osborne Reynolds observed that when the velocity of the flow was low, a simple undisturbed colored trickle was seen to flow along the pipe. This orderly, stable flow in a fluid is known as laminar flow.
So here the idea is that in fact the velocity is going from the left to the right, and when the velocity is not high, you can see that the color part is completely laminar in the system, and then when you increase the velocities, you have a change and instability.
Orderly, stable flow in a fluid is known as laminar flow. However, when the velocity of the flow increases, the colored trickle becomes increasingly unstable. And with any further increase in the flow velocity, a turbulent and violent flow of the liquid ensues. This is called turbulent flow.
So the idea is that at low velocity, you have a regular flow. Then you have instabilities when you increase the velocity, and then you have a transition, and then it belongs to the field of turbulence. And the number which is proposed is called the Reynolds number. So it's a number which has no dimension. It's a product of a characteristic velocity times a characteristic length divided by the viscosity. And what is the viscosity? So it's a number which characterizes the flow. And in the air, it's of the order of 10 minus 5. The unit is square meter per second. And in the water, it's about the order of 10 minus 6. In the water, in fact, the viscosity depends on temperature and on salinity. You can see here 3 curves: salinity 0, like pure water, salinity 15, like in an estuary, and salinity 35, like in the ocean. And you can see that they are very close curves, so it depends on salinity, but very weakly. But it depends more strongly on temperature, because you can see between 0 and 20 and 30 degrees, for example, you can have a change. It's decreasing, and it goes from 1.8 to about 0.8. Then we can also express numbers using Navier-Stokes equation. So first, I will recall what are the Navier-Stokes equation. Here you have the compressed notation, which is shown here. So if it's involved, in fact, notation that I used in math, and which expresses different ways to look at gradients and vectors. So in fact, if you develop this equation, you can see using the partial derivative notation, you have these 4 lines, which can be seen as quite complex, where there are 4 quantities which are unknown. It's a 3 component of the velocity, ux, uy, and uz, and also the pressure. And we can also look at what's happening, because this was for the velocity. We can also look at what's happening when we consider a scalar which is transported by the flow. The scalar is noted here, theta, and we can see the compressed notation, which is here. So d is here the diffusion coefficient, and this scalar can be like a chemical quantity, or it can also be phytoplankton concentration, it can be salinity, it can be temperature. And if you look at, if you consider the developed expression, you have something like here with also a different partial derivative, and also chemical and biological reaction can be added on the right. So if we want to have some numbers to characterize turbulence, so the first number could be the average of these quantities, And then the second moment, so like a variance. So we have the variance of the scalar, or you can also, because velocity is something which is a vector, so you can have 3 variances. And if you add all these 3 variants, you divide by 2, and you obtain something which is called kinetic energy. So this K, which is shown here, is one of the characteristic number that is used in turbulence. Then we have the dissipation. So the first dissipation is the dissipation of scalar variance. The expression is shown here. And then you can also have the dissipation of kinetic energy. So it's an average of different quantities, the square of different quantities, which is shown here, which is a complex expression which can be simplified in some cases with the expression you see just below. So this number, the dissipation, which is noted epsilon, is also one of the numbers that is classically considered in the field of turbulence. So to summarize, you have 3 numbers that usually are given in order to characterize a turbulent flow. You have the Reynolds number, the kinetic energy, and the dissipation. Then just a few words about the models. So in fact, when you have the complicated Navier-Stokes equation that I have shown, you can discretize it using a numerical, making a numerical resolution. And we have many partial derivatives, but they can be approximated using, in fact, differences. And then you can solve it in a grid. And this is called direct numerical simulation of Navier-Stokes equation. With the increase of computer power, we can have very nice pictures like the work which is shown here. And DNS, so direct numerical simulation, is done in turbulence since the 1970s, so 50 years ago. And the present time maximum is of the order of a Reynolds number of 50,000. The problem is that, in fact, the Reynolds number for the ocean is very large because you can compute a characteristic velocity of 1 meter per second, characteristic depth of, for example, 1 kilometer. The viscosity is the order of 10 minus 6. So if you compute the Reynolds number, you obtain 10 to the 9. So it's a very high Reynolds number. And because the computing time is proportional to Reynolds number cube, we can see, in fact, if we want to do a DNS of the whole ocean, we need to have a computing time of 10 to 2013 weeks. It's because, in fact, the work I have shown just before was done during 1 week of computing power of a very powerful computer. So it means if we want to do a DNS of the whole ocean, we need 200 billion years. So it means it's 10 times the age of the universe. So it's not possible. And that's why, in fact, people have as a solution, the solution for this is to average over a larger grid. And the grid size which is used for this is from 100 to 10 kilometers. And sometimes for local modelization, you can find a grid of the order 100 meters or even 1 kilometer. So there is here an issue about scale, because the small scale of turbulence is of the order of 1 millimeter. And if you take a grid of the order of the kilometers, you have a ratio which can be 1 million. So you have a 1 million, a grid which is 1 million times larger than the small scale of turbulence. So it means you have a problem of scale here. And you have the question, can we consider the system at a large scale by performing an average over a large grid size? So what about the small scales? They're not important. You can neglect them. So this question is synthesized here. It means average of Navier-Stokes equation. Is it equal to an average of Navier-Stokes applied to a large grid? Is it the same? So people that are familiar with this will recognize a problem which is linked to linear systems. So this equality that I show here is true for a linear system, but it's not true for a nonlinear system. And Navier-Stokes equations are nonlinear. So in fact, when of course, I don't give here the details, but when we apply this to Navier-Stokes equation, we obtain a new term, which is given here in red. It's called the small scale flux. And so that's, in fact, the solution of what I've shown is that we can model this, but we need to add a flux. So finally, we can say that the average of reality is the model plus a new term, which is a flux. So this new term corresponds to the small scale. It must be taken into account, otherwise the model is not exact. For the present time, in fact, we don't know what are these small scale. So it's something which is classical, is known to be it's called the turbulent closure problem. And all this means that, in fact, the models are not exact because they usually neglect fluxes. They take a very simplified expression for them. And without, in fact, knowing if this simple expression is correct or not. So we can see that, in fact, this is an example from a very nice image from the NASA. So it's a model, it's a modelization, but it's done using a model which is not exact. And so, in fact, we can see, but if you are a bit user, you can see that you can see eddies at a given size, but you don't see small scale eddies because, in fact, in these simulations, there is a problem of small scales. So that's all for models. I hope you know, with this short presentation, a bit more about how turbulence models in the ocean are built and how they work. Thank you.